Hey class, so a few people have asked about problem 103 on the homework, and I think it's a good one to make a video for to give you guys some pointers. So just to kind of unpack what's going on here. So we have a thin rod that we're told has a mass and some length. I'm going to go ahead and on my thin rod, I'm just going to label, let's call approximately here to be my center mass, which means, yeah, my center mass is maybe about here when it's in the vertical position, or when it's rotated up, I should say. We are given the distance d, which is from the end to the axis. So if you notice, the first thing to observe here is that our axis of rotation, which is at point A here, that does not pass through the end of the rod or the center of mass. So we don't have a set moment of inertia equation for that. Bummer, we'll have to do some calculations for that. Okay, that's my first observation. The next thing, we're told when it's moving through the vertical position, so when it's like down here moving at point B, it has some given kinetic energy, which in this case is 17 joules. Your numbers might be different. So it's moving when in the vertical position here, okay, and then it's going to rotate up to a new position shown here. And for part C, we're asked to figure out what this angle theta is. So part A is just asking us what is that rotational inertia. B is asking us how fast is this point at the very end moving when it's vertical. So what is the translational velocity at this point? And then part C is asking us for theta. So let's just take this kind of step by step. Initially, in part A, we're asked to find the moment of inertia. And since we have an axis, A, that's some distance away from our center of mass, we need to use the parallel axis theorem. So to remind you, the parallel axis theorem tells you your moment of inertia, or your rotational inertia, will be equal to whatever the inertia is if the axis were through the center of mass, plus the mass multiplied by h squared, where h is your new distance away from the center of mass. In fact, I'm actually going to change it. I'm not going to call this h. The equation has h, but I'm going to give it a new variable because I don't want us to get confused. So I'm going to go ahead and call it s. No, I don't like s. I will call it t for Todd. Why not? Anyway, so t then, as you can observe, should be this distance from the axis, point A here, down to the center mass. That's the distance that we are away, our axis is away from the axis through the center mass. So if we look at our picture, we should be able to observe that t is just going to be half of the length minus d. So we can get an actual number for t to plug it in. So when you go to find your inertia of the overall rod through the axis at point A, it should be I of the center mass. If you looked at the picture you took from my PowerPoint, you should find that through the center mass, I would be 1/12 ml squared for a thin rod. And now we're going to have to add m plus this whole t, L over 2 minus d quantity squared, and that would give you your new moment of inertia. Okay, cool. So that's part A. I'll let you do the actual math. Part A, I just wrote part A again. Nope, we only have to do part A once, believe it or not. So now for part B, you're asked to determine, okay, what is its linear speed of the very end down here at the bottom? Okay, so we have a rotating object and we want the linear speed of a certain point. Okay, so for that we know that linear speed, the translational speed at the end, or tangential speed, should be equal to omega times r. Okay, well, what is r? Oh boy, we need to label yet another variable. So let's pick a color. Maybe I'll go back to green. So r is going to be the distance from our axis of rotation down to the point that we want the speed. So r is going to be this distance here. So if you notice, r is yet another new distance. In this case, r is going to be equal to the overall length of the rod minus d. All right, so that's r, but we still need to know omega first. How can we find omega? Good question. Well, we know at this point in the vertical position it has a certain amount of kinetic energy, and we know that kinetic energy is equal to 1/2 I omega squared. So, oh, that's easy enough. Omega is just going to be equal to the square root of 2 times our kinetic energy divided by the moment of inertia that we just found. So you can then find omega and plug that in to find V and get a box-worthy answer for V based on the numbers in your problem. Oh, bonus. Okay. That's all fun and good, but part C is where we really get, serious, okay? So I'm going to zoom up a little bit here to make a little more space. And so in part C, we're asked here to determine theta. Oh boy. All right, so I'm going to draw this picture again, maybe in a slightly different way. I'm going to actually zoom in just on the top half. So let's imagine that we take this picture, apparently I'm going back, and let's say, okay, I'm going to just take and draw a zoomed in picture of this part. So I'm going to cut off the very bottoms of my rods. The reason that I'm doing that is because when we think about conservation of energy, we're really just looking at, in terms of gravitational potential energy, the change in height of the center of mass. All right, so what I'm going to do is I'm going to take, I have my rod, oh boy, that is not straight at all. Okay, so I have my rod. When it's in the vertical position, it might be something like this. Again, I'm cutting off the bottom half. So let's say that this is my center of mass down here. I'm cutting off the bottom, and here's my axis A. And then it's going to rotate up to a new point, like this, where again, it looks like about the right length. I'm cutting it off, so this would be my center of mass here, and then this is the angle theta we're trying to find. So what I want to do here now is, if we're trying to figure out theta, I need to look at a triangle, right? And so let's form a triangle right here. I have this triangle. Now, if I can figure out, if we call this side, A, this side B, and this side C, if we can figure out any two of those, we can then use trig to find the angle. All right, so now we need to ask ourselves, how can we figure out these different sides to our triangle? So if we start, let's see, side C is pretty straightforward. That's just the distance from our center of mass to point A, which we already figured that one out earlier. That's just half of the length, L over 2, minus D, because again, D is this distance up here, right? Okay, so we know that side of our triangle. We know this is a 90-degree angle, it's a right triangle. So the question is, what is A? Well, if we look here, we can see that our center of mass increases in height a distance of h. And A is actually just going to be equal to C, which was L over 2 minus D, minus h, this height here that the center of mass changes. So if we can find the vertical distance that the center of mass moves up, we can then find A, which would hopefully help us to find the angle. Because as we can see here, right, the angle theta, the cosine of the angle theta should be equal to A over C. All right, so to find this distance h here, I see my center of mass moving up. I know that it has kinetic energy in this initial situation, so it makes me think of using conservation of energy. So if we use conservation of energy, we have E initial plus work done by non-conservative forces equals E final. There's no work done by outside forces. Our initial energy is just the kinetic energy we start with, 17 joules in this case, and our final energy, since it comes to rest, is just equal to mgh. So our h is just going to be equal to our kinetic energy over mg. Once we get h, we can plug that in up here to get A, which we can then use to get the angle theta. Oh boy howdy. That's pretty good. But it's a tricky one, so that's why I made this video. If you have more questions, go ahead and let me know, but I hope that was helpful. Have yourselves a box-worthy day.